Let's say you're an actual nation that's trying to develop nuclear weapons. You're purposely going to try to extract that plutonium from those samples. Plutonium is a different element than every other element, so therefore you do chemical processing on it to recover the plutonium. And then the non-state actor steals it. There are going to be like trace amounts of contaminants that are left behind. You might have a little bit of the uranium that was left over from the uranium in the reactor. You might have some leftover fission products like the samarium. You've got this mixture of things in there. How do you use that to determine the history of the sample?
Welcome to My Nuclear Life. I'm Shelly Lesher. Today on the podcast, we have Charles M. Folden III, or Cody. He is an associate professor of chemistry at Texas A&M University. He's actually a nuclear chemist who are very handy people to know and have around. This episode is the epitome of what we do around here, a combination of science and history, experiment, and archival work, all based on a little powdery sample of plutonium. Cody and his colleagues set out to age this sample and in the process develop some pretty cool new techniques. We're going to be talking about his group's paper titled Nuclear Forensic Methodology Identifies Legacy Plutonium from the Manhattan Project, which was published a couple of years ago in the Journal of Radioanalytics and Nuclear Chemistry. Cody does a great job explaining what they did, but for more information, I've linked the paper in the show notes. So you published this paper a couple years ago about a sample of plutonium, which you found was among the first kilograms of the element ever made.
Yes.
How did you come across this sample?
Well, it started when my graduate student at the time, whose name was Kevin Glennon, he was doing an internship at Los Alamos, and that laboratory, was deeply involved in the initial studies of plutonium when that element was first discovered. And they have a large amount of this material, enormous amount of it, going back many years. So he happened to be working with a chemist there named Evelyn Bond, who had access to some of these older samples. And he happened to be going through the sort of inventory that they had and discovered a canister that was labeled Clinton plutonium. Now, in this case, Clinton doesn't have anything to do with President Clinton. It refers to the Clinton Engineer Works, which was part of the Manhattan Project. And so this kind of raised some eyebrows immediately, and he started to analyze this. And he actually opened up this container, and there were 4 different samples inside. He did an analysis of all 4, and one of them was really interesting and then became the basis of the paper that we're talking about.
The original plutonium was not discovered at Clinton. What's the origins of just the discovery of plutonium?
Yeah, plutonium was actually discovered in Berkeley using a particle accelerator-based reaction. So at the time, Berkeley had a cyclotron, and they used a beam of deuterons, if I remember correctly, to radiate a sample of uranium, and then they converted that into neptunium, which decayed to produce plutonium. And then they were able to produce some number of micrograms of plutonium that were used for subsequent studies. So it had actually been produced in a particle accelerator-based experiment. The problem is that those particle accelerator-based experiments don't produce enough plutonium to make a very large sample that might have been used for a nuclear weapon, which was the goal of the Manhattan Project.
How much plutonium were they looking to make for the Manhattan Project? So you said not milligrams. Like, are we talking kilograms or?
It was kilograms. And so I don't want to say the number, but the critical mass of plutonium is a known quantity, and it's in the kilogram range. And so they needed to scale this up by a very large factor. And the initial studies, which were done on these microgram amounts, there were things you can do with micrograms in, even in that era, but you needed to really scale this up by a huge factor to the kilogram scale to make it viable for the Manhattan Project.
So this is 1943, I'm guessing? Oh, I got that right?
It was around that era, yeah. So plutonium, I believe, was discovered slightly earlier in the 40s, if I remember correctly. But by the 1943 or so, the Manhattan Project had started to seriously consider designing the fancy new technology of that era, the nuclear reactor. Enrico Fermi had built this demonstration reactor famously at the University of Chicago and demonstrated that a chain reaction was actually possible. And then there was this goal of trying to build a much larger production reactor that would produce larger amounts of plutonium, which then could be sent to Los Alamos for studies on nuclear weapons.
I'm curious about what this sample actually looked like that you found. So it's in a canister, and in the canister, there's 4 samples, but what do these samples really look like?
Well, I wish I could tell you it was something really dramatic, but it was totally the opposite. So unfortunately, the canister was basically rusted out. It had some markings on it about Clinton PU. It had some dates on there, which turned out to be not meaningful at all, which is actually a lesson on don't trust everything that you read. And so you opened up this rusty canister, and there were 4 little vials in it. And in the bottom of each vial, there was a certain amount of just an ugly powder, but it's powder of plutonium. And so I'd like to tell you it was something really beautiful and amazing and well kept, but it wasn't.
So are we talking like a quarter of a teaspoon of plutonium or like an eighth of a teaspoon? How can I imagine the powder?
So in our case, the samples were typically in the range of like tens of milligrams. And so they were actually quite a bit smaller than like a teaspoon, for example. I mean, in many cases, it's like a fraction of a pea. I don't know exactly what,
baking quantity that would be.
Yeah, like maybe the amount of yeast you might put in bread, for example, something like that. Actually, probably less than that even. I'm not a baker, so I really shouldn't comment on that. But it was, like I said, maybe a fraction of a pea, something like that. So a relatively small amount, but it was enough for us to do our analyses.
Wow. So what sort of analysis? Because you're a chemist, you're a nuclear chemist. And usually when I talk about this sort of analysis, I say, well, they did chemistry on it. Mm-hmm. When I tell people they did chemistry, what am I telling them that you did? What kind of chemistry do you do?
It depends on exactly like what analyses you're trying to do. So let's attack this from like 2 different sides. So the first thing is, if you wanted to actually measure the amount of plutonium in this, how could you do that? So there's a couple of ways you could do that. One is to take an alpha spectrum of it. So plutonium has alpha emitting isotopes. You could put that in front of an alpha detector and take a spectrum and then identify the amount of it. So in that case, we would need to prepare the sample, which needs to be very thin. So one of the things we would do is like dissolve it up in acid. So for example, one of the classic things we do is that we try to convert the solid sample, this powder, into a liquid sample by dissolving it in acid. So just like acid eats away iron, for example, it will dissolve up plutonium at the same time. So you make this liquid sample, and then you could use that liquid sample, for example, no pun intended, to do a mass spectrometry on, for example. One of the other things we were interested in, which I'm sure will come up in a minute, is that we were trying to analyze the amount of what are called fission products that are present in the sample. So when plutonium is produced in a nuclear reactor, one of the things that the reactor does is it creates fission products as it operates. And then as a result of that, these fission products can be left behind in the plutonium, and we wanted to analyze those. So one of the elements that we really cared about is the element samarium. So the problem is that samarium has very similar chemical properties to other elements that are nearby it on the periodic table, and the lanthanides, we would say. So one of the things we have to do is when you talk about doing chemistry, the second part of this analysis is trying to extract out the samarium specifically. So what we would do then is we would use a technique which is called column chromatography. So if you've ever watched like one of these forensic TV shows, for example, they frequently talk about like sending it through a gas chromatograph. Okay. We do a similar technique where we run it through what's called a column, and then different elements move through the column at different rates. And by carefully choosing the conditions of this column, we can identify when the samarium is going to come out. And then we, at that right moment, collect that sample of samarium, and then we analyze that using mass spectrometry. So for us, the chemistry is, like I said, maybe 2 ideas. One is dissolving the sample, and then 2 is doing the specific techniques we use to extract the specific elements that we actually care about. So just to be clear, I made this analogy with gas chromatography. We didn't actually do that as part of our study. We use what's called liquid phase chromatography. So there's a special chemical that was developed back in the 50s that if you mix it with a group of these lanthanide elements and you put this in a what's called column, the elements will move through at different rates. And the element that has the highest atomic number moves the fastest. And the one that has the lowest atomic number moves the slowest.
Seriously?
Totally, yeah. This is a very classic technique.
What sort of magic liquid is this?
It's called alpha HIB, alpha hydroxy isobutyric acid. But
how would you discover this? I'm sorry, I'm stuck on this. How would you discover something like this?
These idea of separations, trying to extract one element from a mixture of elements, is a classic problem in chemistry and has been around for decades and even centuries in some cases. I think what had happened was that just this was a key problem in science. And especially once nuclear chemistry really took off as a science, this became a serious thing, especially once nuclear reactors came around. This problem of separating these fission products was like hugely important. And some people, the one that I remember, his name was Greg Chopin, who used to be a chemistry professor at Florida State. I believe he was the one who really developed this idea of this alpha HIB. And just by thinking about the problem, he said, okay, I need something that complexes with these elements in a certain way. And after presumably a lot of tries, he came up with this one that succeeded in doing this separation. And so I think it was a combination of a lot of clever thinking and then a lot of hard work as well.
I mean, it's like magic.
Oh, it is. I mean, this, except for the fact that it's science, right?
I mean, it's science, but that's why science is magic sometimes.
Yeah, I mean, for us that are in the business, this alpha HIB is like a critical thing. And the fact that it can separate these lanthanides is just extremely powerful. And we're lucky that somebody discovered this to make it available to us. It's an amazing technique.
Okay, sorry, I got off on that tangent.
No, that's okay.
Because that just, that's, I can just see it like kind of like a layer of soil and you can just like pull it out. I'm sure that's not what it looks like, but that's what it seems like to me.
Well, there's a lot of similarity actually to like when rainwater moves through soil, like the different materials in that soil will move through at different rates. Or if there's any like contaminants in the water from the rain, they move through at different rates. It's a very similar idea. Yeah.
So why were you looking for samarium specifically?
Okay, so we had actually been working on this question of forensically analyzing plutonium for several years. And I should also give a shout out to my colleague, Sunil Chirayath. I'm in the chemistry department at Texas A&M. He's in the nuclear engineering department at Texas A&M. And we had this collaboration for several years to try to understand what properties of plutonium can we measure that would actually tell us something important. And one of the things that he had done is that he's a simulations person and he's an expert on simulating nuclear reactors. And he had run simulations of reactors and determined that if you could determine the ratio of different isotopes of samarium specifically, that would tell you something about the reactor itself. It turns out it tells you about the energy spectrum of the neutrons in the reactor. So we had identified samarium 149 and 152 as isotopes that would be interesting if you were trying to do a forensic analysis of plutonium, if you want to know what kind of reactor produced it, for example. And we actually had a list of other isotopes that we cared about as well. So plutonium isotopes were on the list, cesium isotopes were on the list, barium was on the list, and then samarium was on the list. Samarium specifically, the isotopes that are produced as fission fragments in a nuclear reactor, have the exact right properties to fit the criteria that we had developed. And so we knew samarium would be an important element. So my student Kevin went through and developed a process for extracting the samarium out of the sample using alpha HIB. But it was really this combination of simulations and chemistry that allowed that to succeed.
I'm glad you used doing chemistry the same way I do. So that still doesn't get us to how it's from the Clinton engineering reactor. That just tells us its reactor produced plutonium.
Okay, let me give you some more insights into the analysis we did, and then we'll see how we get to Clinton. Okay, it's going to take a couple of steps. So one thing that we're interested in is knowing how old the sample is. So for example, we want to know like what reactor produced it. How old is it? Okay, so how do you determine how old plutonium sample is? So what you do is you assume that the chemists that prepared the sample chemically purified it pretty well. So what that means is that they did a very good job of trying to recover the plutonium and get rid of all the other elements that are present in it. So at that point, what happens is you take advantage of the fact that plutonium is radioactive. So plutonium is an alpha-emitting isotope. There were two different isotopes of plutonium in our sample, 239 and 240.
Okay, and you found that out because you looked at the alpha spectrum.
Right. And so we can look at alpha spectrum. You can also do mass spectrometry and determine the amount of 239 and 240. Okay, so you measure that. The problem is that doesn't tell you how old the sample is. It just tells you how much plutonium you have. I did say that the chemists that prepared the sample should have done a very good job of removing any other elements. One of those elements that they try to get rid of is uranium. So why is uranium important to this story? So if you make plutonium in a nuclear reactor, and the reactor is a giant neutron machine, those neutrons interact with uranium and get captured. They convert uranium into heavier isotopes of uranium that then radioactively decay to produce plutonium. So theoretically, you want to get rid of all this uranium that was present inside the reactor. Okay, so chemist does a purification, gets rid of the uranium. Then what happens is that the plutonium starts to radioactively decay immediately and decays back to uranium. So if you can measure the ratio of the plutonium that you have now to the amount of uranium that you have now, that will tell you how long the sample has been decaying. And because we have two different isotopes of plutonium, we can do this measurement twice to give us some sort of redundancy in the measurement. Okay, so once you've done this measurement and you have your age of the plutonium, what we found out was that it was from early 1944. Now, what's interesting about this story is that plutonium, a milligram amount of plutonium, had to be produced by a nuclear reactor. However, in 1944, there were only a couple of different nuclear reactors in the entire world. So how did we get to Clinton plutonium? So we went through the list.
Oh, I have a question.
Yeah.
How were there more than one plutonium reactors in the world? I thought we were the only one developing the bomb.
Well, the United States had a couple of different nuclear reactors at the time, and we'll go through the first three that were developed, and I'll tell you how we settled on the Clinton reactor.
Ah, okay, because I didn't know. I thought it was just, oh, okay, I know where we're going.
I know where we're going.
All right.
I'll go ahead and tell you the answer. So,
yes, please.
Okay, so let's
fill
go.
everyone else in.
Yeah. So the first reactor I mentioned earlier was this one famously developed by Enrico Fermi at the University of Chicago. That was sort of a demonstration reactor. It was not really designed to produce a large number of neutrons and do this quote unquote transmutation of uranium into plutonium. It was designed to prove that you could actually make a chain reaction. And that was its goal. So it only ran for a short amount of time. It did not have a high power and did not produce any significant amounts of plutonium, for example. But afterward, the reactor was scaled up significantly, and there was a much larger reactor built at this Clinton Engineer Works, which became Oak Ridge National Laboratory in eastern Tennessee. So there they hired a corporate contractor to come in and help design a much larger reactor that could actually produce larger amounts of plutonium that would then be sent to Los Alamos for additional research. So that reactor was called the X-10 reactor, what we would now consider to be a medium-sized reactor, and it was operated in such a way that it was designed to produce plutonium. Now, the thing about this is at the time, they had identified that a certain isotope, plutonium-239, could be viable for use in a nuclear weapon as the main fuel. Okay, so what they did was that they operated the reactor in a way that tried to maximize the amount of plutonium-239 at the expense of all other considerations. However, in practice, that was not perfect. And what happened is, as soon as you produce some plutonium-239 in a reactor, it will start to capture some of the neutrons that are present in the reactor and produce plutonium-240. And what happened is that a tiny amount of plutonium-240 was being produced inside this X-10 reactor in Oak Ridge. And as a result, there was a tiny amount of plutonium-240 that was present in the sample. And by tiny amount, I mean a really tiny amount. It was like 0.05% of all the atoms of plutonium were this plutonium-240. And I'll come back to the significance of that in a minute. So this tiny amount of plutonium-240 is present, but it was enough for us that we could actually analyze. And so it's just the natural property of a reactor that it will try to create heavier isotopes of the elements that are present through this neutron capture process. And so as a result, we had two different isotopes of plutonium available, and we were able to analyze both of those and use this process called chronometry to get the age of the sample.
Wait, what's the third reactor?
The third reactor that was available in the early 1940s was called the B reactor, which was built at Hanford in Washington State. So this was a much larger, again, scaled up, larger reactor that was designed to produce significant quantities of plutonium, the kilogram quantities that would be needed for a nuclear weapon. And if I remember correctly, the Hanford B reactor was the reactor that produced the plutonium that was used in the weapon that was used against Nagasaki at the end of World War II. So the question was, okay, out of these three reactors, which one was likely to have produced the material that we actually analyzed? So first of all, we eliminated the original Chicago reactor, the Fermi reactor, which was called CP1, Chicago Pile 1, in part because its power level was so low and it operated for such a short time that it should not have produced any significant amounts of plutonium.
Okay.
Then the other question is, could we eliminate the B reactor? And that gets to be a little bit more complicated question.
Right.
So one of the things that we tried to do was to determine a property called the burnup. So burnup is a measure of how much energy has been extracted from uranium inside a nuclear reactor. All right, so there are different techniques for doing this. There's the easy way and the way that we actually had to do. So the easy way is that if you can acquire a sample of uranium straight out of a reactor, it's going to have some uranium, some plutonium, and some fission products. And then you go to a nuclear engineering textbook and you look up, okay, how do you determine burnup? And they tell you measure the amount of this isotope relative to the amount of this isotope and reference this chart, and you'll get an answer.
But in that case, you already know how old it is.
Right. In that case, you might have some idea of the history, the provenance of that particular sample.
Okay. But in your case, you don't have that information.
We didn't have that, so we had to do it the hard way.
Okay.
So the hard way is you collaborate with a nuclear engineer and do a simulation of the reactor and then try to determine the properties of the sample. Its burnup, how long it was in the reactor, how long it's been out of the reactor. What you do is you simulate many different reactors under many different conditions, and then you compare your measured data against what the simulation tells you. And we had a technique for doing that, and we came up with an answer that said the burnup was a certain number of what are called megawatt days per ton. So if you pay your electric bill at home, that's in kilowatt hours. A megawatt day is just a bigger unit of energy, and this is how like reactor engineers describe the amount of power. So it's a certain number of megawatt days for each ton of uranium in the reactor. And when we did that, what we found was that the burnup was extremely low. Now, why is that significant? This B reactor at Hanford was designed to produce a large amount of plutonium for an actual nuclear weapon. It was unlikely that the amount of burnup that we observed, this really tiny amount, it was unlikely that this B reactor would have been operated to produce such a low amount of burnup. So as a result, we were able to partially eliminate the B reactor as the source of this material.
I'll ask the question. Why is the small amount of plutonium-240 important?
So it's important because, let's say today you were to go to your local nuclear power plant, and let's say they allowed you to take a sample of plutonium out of the core and analyze it. What you'd find—
that'd be great.
That'd be cool, but they're
that'd
not
be
going to let
fun,
you do that.
yeah.
But
okay.
What you'd find is that it probably has a mixture of different plutonium isotopes. Plutonium-239, which is the main one for maintaining the chain reaction, at least among the plutonium isotopes. A certain amount of 240 that's produced via neutron capture on the 239. Maybe some 241 that's produced via neutron capture on the 240. Maybe some plutonium-238 that's produced in an ancillary reaction. We call it N2N. And there's going to be some distribution. If you go to our sample from the Manhattan Project, what you find is that it's almost entirely plutonium-239, 99.95%, and just a tiny amount of plutonium-240. So that is significant because if you were trying to produce plutonium in a power reactor, you would allow the reactor to operate for a long period of time, and the interaction of the neutrons with the plutonium would cause you to produce a wide variety of plutonium isotopes. Ours did not have that. It was almost perfectly isotopically pure. That is a sign that it was intended for a nuclear weapons program.
Oh.
It's also important because it tells you that it was designed for a nuclear weapons program in the early days of nuclear weapons programs. So nowadays, this is not a secret, I think it's okay to say, nowadays the amount of, or the purity of the plutonium-239 can be much lower and a nuclear weapon will still work properly. However, in 1944, nuclear engineers did not know that, and so they said, we're going to hedge our bets and make the 239 plutonium as isotopically pure as possible. So the fact that we had such a tiny amount of plutonium-240 meant that it was from a nuclear weapons program in the early days of the nuclear weapons program, which also confirms our chronometry, which tells us that it was also from 1944 range. Now, there's another thing that we had up our sleeve, which was that we were able to find historical documents that described shipments of plutonium from the Clinton reactor, the X-10 reactor in Tennessee, to Los Alamos. So my student was at Los Alamos at the time. He had access to their library, and he went through and did this long literature survey looking for documents from that era about shipments of plutonium from Clinton to Los Alamos. And with a lot of work, he was able to dig out a variety of different documents describing the dates at which this occurred. And if you look at the dating of our chronometry, if I remember correctly, it's several months, I think a sizable fraction of a year, before the B reactor also started to operate. So between the burnup that didn't match, the dates that didn't match, and the historical documents suggesting it came from Clinton, that was sort of the combination of things that allowed us to determine that it had come from the X-10 reactor in Tennessee.
That's how you determined it was one of the earliest samples, because it was a sample from X-10 before the B reactor went online?
Yes. It looked like the date that we observed was before the B reactor came online, if I remember right. Mm-hmm.
So is it the oldest sample in the literature?
Okay, this is an interesting question. So the short answer is that may not be true. But it's partly because several years ago, there was a very tour de force analysis of a plutonium sample done by my colleague, John Schwannis, who at the time was at Pacific Northwest National Laboratory. He's now at Penn State. He was actually working with some material that had been discovered in a dump, basically. But it turned out that it was plutonium. And when he did a forensic analysis of it, he determined that it was also from the early 40s, also from the X-10 reactor in Tennessee, and had somehow ended up in a waste dump.
You mean like a dump?
I don't think it was like your landfill, that would be near your home, for example. It was in some sort of storage location specifically for those sorts of materials. But
kind of like a surplus area.
Something to that effect, yeah. And now I was not involved with that research, so I don't know every detail of it. But to my understanding, it was somehow had basically been forgotten about. So they do this forensic analysis of it, and they determined that it's also from the early 40s, also from the X-10 reactor, but unfortunately, their result had a relatively large error bar on it. So our result had a smaller error bar, so I think that at some level we were more convincing. However, their sample is clearly within the same range of dates as ours. And you're somewhat limited, right? Because you want to say, or I'd like to tell you, hey, we had the earliest sample that is out there. The problem is that we know when plutonium was discovered. We know when reactors started to produce plutonium. So there's only so far back in time you can actually go. And our error bars overlap their error bars, so you can't actually say which one is older. So we're kind of in I don't know what's the word here, an undecided situation. Is theirs older or is ours older? You probably can't say.
Just looking at it, though, it seems that Los Alamos would have look, we know Los Alamos had the first samples.
Oh, for sure. Yeah.
Historically. So it would make sense they would stay at Los Alamos. But who knows? They would travel. They had airports, and they would just take little private planes to each lab. So who knows what happened to these things?
Yeah. They did get distributed around, right? They were samples sent to Los Alamos. Some of these original cyclotron-produced samples actually ended up at a laboratory in Chicago called the Metallurgical Laboratory, which tried to study the chemistry of plutonium. And then some samples got sent to Hanford in Washington State. So once the project got moving, there were samples moving around the country pretty much all the time.
Which is crazy, because it's just such a tiny little amount, you wouldn't even know it to look at it.
Oh, yeah. And the speed at which this was scaled up was also incredibly impressive as well. They went from microgram amounts to kilogram amounts just within a couple of years. Amazing accomplishment.
You had mentioned that you were able to remove the samarium.
Yes.
Are you able to reconstitute the plutonium? So you're doing this chemistry, you're pulling things out. Are you able to make it whole plutonium again at the end? I don't know much about chemistry.
Well, the short answer is theoretically, if you were able to hold on to everything, you might be able to put it all together. The bad news for us is that the process of doing the analysis itself actually hurts the forensic value of the sample, for example.
Wait, you're telling me that you destroyed the oldest sample of plutonium?
Well, the problem was that the short answer is we did have to dissolve it up, okay? And when you put it into a mass spectrometer, it's not readily available to be recovered. And the problem is also that the amount of samarium that we have access to, I don't remember the exact amounts, but it's probably in the microgram range, for example. So we need a large amount of sample in order to recover the tiny amount of samarium. All right. So the thing was that, did we destroy the sample? Yes. However, as part of our analyses, and we can talk about this in a minute, we were able to estimate like how much plutonium had been produced up until that time. And the answer was about, if I remember correctly, 1.4 kilograms. So we used up 60 milligrams of 1.4 kilograms of material. So that material is out there somewhere, but unfortunately, the analysis we do is what's called a destructive analysis. It requires that you destroy the sample in order to conduct the analysis. Now, we also start off with what are called non-destructive analyses, but unfortunately, some of the analyses are destructive. Mm-hmm.
I think that's what you should put on your resume.
That I destroyed the oldest sample of plutonium out there. I don't know. I don't know if I want to be known for that.
How did you know what contaminants were in the sample?
So the thing was, at that time, there were only a couple of different chemical processes available for purifying plutonium. I mean, it was a brand new element. Chemists had been studying it, but hadn't fully, worked out all the details or the most important details of its chemistry. But they had figured out a couple of different techniques for trying to purify it. So based on the known techniques at that time and some historical documents we found listing the contaminants that were present in the sample, we went through and tried to look for each of those different elements. We actually did a wide range of mass spectrometry and tried to identify, okay, which elements are present in this particular sample. So I believe there in the documents from that era, there were 13 different contaminants listed. And I believe we identified 12 of those, which was a good sign because it was a pretty good matchup. And then also because mass spectrometers in the 21st century are more sensitive than ones from the mid 40s, we were able to identify a number of other elements that were also present in the sample. And then we were able to correlate those to the processing techniques that existed at that time. And it kind of added up in a way that made sense.
What are some real world applications? So I'm thinking, say a material is found in a lab by like a non-state actor, and it's thought to be plutonium. Could you get this sample and figure out, well, you could figure out it's plutonium, but could you figure out what reactor supplied the material?
Okay, so this is a very interesting question. So the real world application here is that, especially during the 90s, after the end of the Soviet Union, in Europe, every couple of years, like every 18 months or something, there would be a sample of either enriched uranium or plutonium or something that would be interdicted by police at a border crossing somewhere, especially in Eastern Europe. This came up a lot. So, for example, let's suppose you're a police officer, you stop somebody, turns out they've got radioactive samples in their car, and police nowadays now have access to Geiger counters, and so they can detect things that are radioactive in many cases. They acquire that sample and they send it to your lab to try to analyze and say, where did this come from? I mentioned earlier that if you had a sample of material that was like straight out of the reactor and had no chemical processing at all, that's largely a solved problem. You just go to a nuclear engineering textbook, look up the answer on how to determine its properties, and go from there. The problem that we started to solve was a more difficult one, which is that suppose the plutonium had been chemically purified. So in principle, let's say you mentioned non-state actors. Let's say you're an actual nation that's trying to develop nuclear weapons. You're purposely going to try to extract that plutonium from those samples. Plutonium is a different element than every other element, so therefore you do chemical processing on it to recover the plutonium. There are going to be like trace amounts of contaminants that are left behind. You might have a little bit of the uranium that was left over from the uranium in the reactor. You might have some leftover fission products like the samarium that I talked about earlier. You've got this mixture of things in there. How do you use that to determine the history of the sample? Okay, so long story short, like I mentioned earlier, my colleague did a large number of simulations, and then we compare the measured isotopic ratios, amounts of different isotopes, to the predictions of his simulations and then come up with the properties that represent it the best. Okay, now what actually comes out of the analysis? I mentioned earlier the burnup. That's like how much energy was extracted from the uranium. That's a useful thing to know, but it doesn't tell you which reactor it came from. You can determine the time since the irradiation ended. So how long has it been since it came out of the reactor? That is something that can be determined via that. But that also does not tell you what reactor it came from. There is one other piece of information, though, which is that one of the things that comes out of our analysis is the class of the reactor that produced it. So, for example, if you build a reactor in the United States, typically we have certain ideas about how a reactor should operate, and they're built by reactor engineers, and they operate a certain way. If you go to Russia, for example, they have different reactors that operate on slightly different ideas, and those differences in the reactor physics actually are reflected in the amount of fission products that you see and the types of fission products that you see, the different isotopes that are present. So the ratios are different in a Russian reactor rather than an American reactor. And so you can actually say that the class of reactor that produced this plutonium was this. Now, can you describe or determine the exact reactor? No. I would still rate that as not viable yet. I will say, like back in the, I think in the 2000s, there was a movie called The Sum of All Fears, and I don't know if you saw this, Shelly, or not.
Oh, yeah.
Yeah, so there's a scene in the middle of this where they're basically doing a nuclear forensic analysis, and the scientists who are talking to each other are saying, oh, it came from this reactor, and specifically maybe like the top edge or the outer edge of the core, for example. I would still rate that as in the realm of Hollywood. We don't have that level of capability. But we can exclude classes of reactors. And so, for example, you can exclude, it's not an American style reactor. It's not a British reactor. It's not a South Korean reactor or Japanese. You can eliminate possibilities, and then that narrows it down to a certain class, which in many cases narrows it down to a certain country. And at some level, that is useful information by itself.
That is useful information. You wrote this paper on the provenance of this plutonium sample being from the early 40s, the Manhattan Project. Is this a problem that you continue to work on, trying to figure out the provenance of plutonium?
Yes, we are actually. And so one of the things that my collaborator, Professor Chiraya Sunil, is working on is that he's been trying to adapt these techniques using machine learning. So when we were starting our project, what we did is we had a graduate student named Jeremy Osborne who worked on the reactor simulations, and then the reactor simulations tell him the amounts of hundreds of different isotopes that are produced in the reactor. And he went through and decided on some criteria and tried to come up with which isotopes would actually be useful for learning the things that we want to learn. And so a human being very tediously went through and teased out of these hundreds of different possibilities the 9 or 10 isotopes that we would actually care about measuring that would tell us something useful. So another student in our group, Patrick O'Neill, has been working to try to use machine learning to automate this process. And I believe that work has not been published yet, so I don't want to say too much about it. But I believe that using those techniques, he's narrowed it down to like 5 or 6 different isotopes that would be useful to measure that could tell you equally good information. And so that's kind of the next generation of this, is using machine learning to try to automate aspects of the analysis. In part because one of the problems we have in nuclear forensics is that there are 2 different types. There's what's called pre-detonation and post-detonation. And what does that mean? So the detonation is if there's a nuclear attack on the United States, either by another country or by a terrorist group, that would obviously be horrifying, but there's going to be a lot of pressure to know as soon as possible what happened. All right. So one of the problems we have in nuclear forensics is that the speed of our analyses is still not as fast as it needs to be. And this is one of the things that we're also working on in my group, is to try to increase the speed of the analyses, because the president is going to want answers to very important questions within hours yesterday. And the current speed at which we can do things is just maybe not fast enough. So these are problems that we're working on, trying to improve the simulations using machine learning to understand the results, and then also trying to speed up the chemical analyses, which is an ongoing problem as well.
But you can only speed up chemical analysis so much. I mean, Don't chemicals have a rate in which they do their work? I mean,
They do, but part of it is, let's suppose that the worst were to happen and there were a nuclear terrorist attack. Okay, and somehow we sent in someone to go and collect samples from the blast zone. So, okay, how quickly can we get those to a laboratory that's ready to go? How quickly can we get chemists together to be ready to analyze those samples? Just making sure that we have all the chemicals ready to go, all of our reagents, having all that stuff ready. Can we increase the limits of detection on, say, a mass spectrogram so that we can get by with smaller amounts of sample, which might be easier to work with? These sorts of things. So we're kind of looking at this from all sides and chipping away at it. Can we reduce the time from getting a sample prepared from 48 hours down to 24? That's one question also. And part of it is just that the preparation needed to make the samples ready to go into the instruments is not trivial. And speeding up those preparations is a key area of research as well.
Wow. Okay.
So yeah, we've sort of come full circle from all the way from the Manhattan Project all the way to the 21st century on this.
Right.
Yeah.
Right. So besides kind of making things faster, is there research being done to try to be able to pinpoint the reactor that produced a sample? Is that important, or are people happy with just the class of reactor?
I mean, there's always an effort to try to provide more information. And so knowing the specific reactor is something people care a lot about. The thing that we're limited by is the publicly available information that's used to create the simulation. So one of the sources of uncertainty in this sort of analysis and the way we do it is the design of the simulation of the reactor. So as best we can, we try to take publicly available information and recreate the reactor in a simulation, in a computer. So the problem then is that if you have any uncertainty about what's the size of the reactor, how big is the core, what are the materials that surround it, that's actually an important one as well. What's the enrichment of the uranium? These things actually start to add up and create uncertainty, and then that blurs the lines from one reactor to another. So if you wanted to know, like, was it reactor A or was it reactor B, you'd have to have very detailed nuclear engineering information about reactor A and reactor B. And you can probably imagine if you're a country that's trying to produce nuclear weapons, you may not have any publicly available information about the reactor that you're operating. And so that becomes sort of a limiting factor. As best we can, we're trying to work around that, but it's not a small problem.
Right. And if you are trying to hide your nuclear program, that's definitely not information that you're going to freely give.
Right, exactly. And so that's a challenge for our technique, is that we have to develop what we call the library of reactors, and collecting the information about them, it's not a small problem. For many reactors in the US, there are filings with the Nuclear Regulatory Commission. In some cases, we can use some of that information to give us, information about the reactor. In some cases, we can make some educated assumptions about how it's likely operating, but it's a real problem. You'd have to have very detailed information to really pin down one reactor versus another.
Who funds your work?
So right now, our funding for nuclear forensics, at least in my group, comes from something called the Nuclear Science and Security Consortium. So the NNSA now has this model where they fund consortia of universities to work on problems. So we're part of this NSSC consortium that's based at UC Berkeley. We're one of the collaborators, and the work we do is nuclear forensics. And then we were also lucky enough just recently to get funded via another consortium, which is starting in the next few months, called the Consortium for Nuclear Forensics, which is based at the University of Florida. And so obviously, based on the name, that's going to have a very heavy focus on nuclear forensics. And then, a lot of the topics that we talked about are going to be within the scope of what they're doing. We're going to try to work on rapid turnaround forensics, trying to make the speed of things faster. And I'm hoping to fund a nuclear engineering student to continue the work on the machine learning, for example. So at the moment, it's mostly the Department of Energy.
It sounds like a really exciting area for students to get into.
This is the thing, is that we have been pretty lucky where in the last 10, 15 years, there's been a lot more recognition of the importance of funding nuclear science and nuclear chemistry and radiochemistry because of national security issues. And especially now after the war in Ukraine, the concern about nuclear weapons has vastly increased. And the reality is, whether people are opposed to nuclear weapons or not, the reality is that in the United States, that is the linchpin of our national security strategy. We need people that are trained in nuclear science to work on those, to work in nuclear medicine, to work in other areas, fundamental research. And so there has been this renaissance of support from the federal government for nuclear science in the last, 10 or 15 years. This is definitely attracting students. And I think the other problem, which I might mention while we're talking, is just about it's so important that we educate students about nuclear science and, of course, my field, nuclear chemistry and radiochemistry, because I think a lot of students are really interested in it. They just don't get exposed to it when they're in college. In physics, for example, many universities teach nuclear physics, even if they don't have a nuclear physics research program. But in nuclear chemistry, the number of programs is much more limited, and the number of students that get exposed to it as undergraduates is much, much lower. And so it's very important that they learn about nuclear science, nuclear chemistry, radiochemistry, and the importance to our country and our society and our economy, so that they will, become the next generation of nuclear scientists and engineers.
This is such an interesting project because not only are you doing the science, but you're also doing the history of the science. There was a lot of archival work involved.
That's what's interesting as well. I like to say if I hadn't become a scientist, if I didn't have a degree in like a technical field, I think I might have gone to college to be a historian. Like I was always interested in history. And I think a lot of nuclear scientists are especially interested in the Manhattan Project because of the significance for the war, the enormous resources that were put into it, the secrecy involved, the scientific discoveries that were made. It's really amazing how like all these things sort of came together in this project. Like you said, the archival work, the technical aspects of it, the connection to history. It's been really fascinating. And I will admit, there was a certain amount of luck involved in getting access to such an important sample, in some cases through dumb luck, but it was really fantastic. And it turned out great for us. And we did a lot of very nice analyses on it.
Yeah, it was a really fun paper to read. And I'm going to link it for our listeners.
So the end result is that we were able to compare historical documents again versus the actual sample and come up with a compelling story about the history of the sample.
Okay, that's so cool. It's just a giant puzzle to put together.
That's the thing. It's like you have so much information, but at some point it does start to add up into a story, right? And once you've got overlapping information between, when was it produced? Okay, what reactors could have produced it? Do our simulations agree with that reactor? They do. Do our chemical analyses of the contaminants agree? We do. And it's kind of like it's like a mystery in some sense.
Thank you for listening, and thanks to Cody for explaining what doing chemistry actually means. Stay tuned for his acknowledgments, as science really is a team effort. If you would like to know more about our podcast, please visit us at mynuclearlife.com. Until next time, I'm Shelly Lesher, and this has been My Nuclear Life.
I want to thank our collaborators on this project, especially my long-term collaborator, Sunil Chirayath from the Texas A&M Department of Nuclear Engineering. He's been an amazing partner in this over many years. I also want to thank Todd Bredeweg and Evelyn Bond at Los Alamos National Laboratory for their work allowing us to access the sample and take advantage of their facilities. The students that worked on this project, I mentioned Jeremy Osborne, who did many of the initial analyses. Matthew Sweeney did a number of important analyses along the way. I also want to thank the students who were directly involved on this, Kevin Glennon and Patrick O'Neill, who put a huge amount of effort into this project and really made it happen. And so thank you to everyone. It was a great collaboration, and I really appreciate all the work that you did on this.